So, today our topic is momentum. We will learn about new physics quantity, momentum, also impulse, and law of the conservation of the momentum. So that is our learning intention today, to learn about those things. Now, momentum, definition. For momentum, we're using a lowercase letter p, and momentum equals mass times velocity. It is important, it's not speed, mass times not speed, by velocity. What difference it makes between speed and velocity?
Rate of change.
It's displacement over time.
Velocity has direction, speed doesn't. So momentum has direction, and it will be very important to take the direction of the momentum into the account when we do the solving. You might ask, why we need to introduce a new quantity? We already have velocity, mass, why we need to multiply them and make a new quantity? But the thing is that this quantity, momentum, is always conserved in the interaction of the two. In the closed system, what does it mean closed system? So we account for all interacting objects, and the total momentum will be always conserved. So we have the final momentum will be equal, total final will be equal to total initial momentum. And this is one of the most fundamental laws of the nature, which holds always. Even, for example, in unit 4, you will be learning about, for example, collision between a particle of light, photon with electron, still momentum will be conserved. So it's conserved always, one of the most fundamental laws of nature. That's why we need this quantity momentum. Now, example. For example, let's say a student with a mass of 60 kilograms coming late to the class and running towards the class with a speed of, let's say, running very fast, 7 meters per second. What will be the momentum of this student?
420.
Yes, 60 times 7 equal 420, and there is no special unit for momentum. Mass measured in kilograms, speed in meters per second, so it will be 420 kilograms times meters per second. In a couple of minutes we will see that we can use another unit for momentum, Newton times second. And I will, because it's like shorter, I will be using predominantly this. Let's see where it's coming from, Newton times second, which is exactly the same as kilogram meter per second. Let's recall second Newton's law. F net equals what?
MA.
Ma. Now let's recall what is acceleration. What is acceleration?
F over M.
V minus
Definition, what is
Force
acceleration?
on mass.
V minus your
It's a rate of change of velocity. It's a acceleration, final minus initial velocity over the time over which it happened. Or, so this is a change, and for change we're using delta, triangle, so we can write delta V on t. That is acceleration. Definition of the acceleration, rate of change of the velocity. Let's substitute it here. So you get F equal m times change in the velocity over time. Let's move time to the left-hand side. Ft equal m change on the velocity. If mass not changing, and in the school curriculum we're considering only cases when mass not changing, can you think about the example when mass will be changing?
Something's melting or like heating?
No, related to motion.
Oh, like-
By the way, when something melting, mass doesn't change. The state change, but not mass. When something moving, yes.
If you've got a car that's burning fuel, then we're getting rid of mass because it's fuel.
Yes, if you will be a little bit more developing this idea. Yes.
If you've got a raindrop and it lands on a window and it goes down and loses its mass on the window.
Yeah, you know, but the most simple example is the rocket motion. Is the rocket motion. Rocket moving, burning fuel, and throwing it back, and also moving forward. And so mass of the rocket in the flight changing. But the mathematics involved is too hard for school level, so we're not considering that. No, by the way, who will be doing specialist mathematics, unit 3-4 will be able to solve equations for related to the rocket motion, but only that. So, as mass not changing, then m mass times change in the velocity, we can say that it's a change in the momentum. And now we get second Newton's law rewritten in terms of the momentum. It's a second Newton's law, just written in terms of the momentum. And this quantity, force times time, has a special name. It's called impulse. It's called impulse. So impulse equal change in the momentum. And because units on the left-hand side will be Newton times second, and we have momentum on the right, that's where it's coming, that we can use for measurement of the momentum, we can use Newton times second. Yes?
But you said that the momentum equals the initial momentum, so the momentum doesn't change. So how can there be a change in momentum?
Excellent question. And now let's have a look into the conservation of the momentum and how it will be not contradicting the when you're saying about the change. Very good question. Thank you. So let's consider this equation. Okay, I will need some assistance from the back. Now, so if two balls will fly toward each other, each of them will have momentum, right? Okay, you need to throw the ball so that it will collide with this. Okay, let's try. Okay, throw the ball so, yeah. Okay,
Wait, so we're both throwing at the
we
same
need,
time?
yeah, so they need to collide.
This is the angle of trajectory?
Well, come on, let's
You
go.
throw first.
No, because it needs to collide closer to me, so you
Okay,
throw
ready?
first.
Go.
Missed. Second attempt.
You throw. Okay, ready?
No, no, we need to collide here. So throw.
Raise up.
Now, when they collide, does momentum of each ball change?
Yes. Yeah.
Yes, but the total remains the same. That is the thing. When two objects or more collide, momentum of each individual object can change. But total momentum stays the same. Or if I throw this ball into the wall, or into the table. No, there's no appropriate wall here. So, what happens with its momentum? It's obviously changed because velocity was one direction, then into the other direction. Or another example, we have car collided with a tree. So we have a car.
So isn't it just if there's acceleration and momentum change?
And you have a tree, and car has velocity Vm, or initial velocity, let's be u, and car hit the tree and stopped. So, does momentum of the car change? Change. How the momentum will be conserved in this case? Goes into the tree. And tree happens to be fixed to the earth. And through the tree, it's passed to the earth. That's why why we don't see any changing of the motion of the earth.
Small force on really big mass.
Very big mass. Let's do the next calculation to see.
Are you saying that the Earth technically moves when you hit it, sure?
Yes.
Okay.
But let's consider the next situation. Let's take all cars in the world. Let's take, I don't know how many cars in the world, let's say 1 billion cars. So 10 in the power of 9 cars. Including trucks and all cars. And let's say average mass of the car, again including trucks, let's say average will be, I don't know, 2 tons, 2,000 kilograms. Times 2,000 kilograms. So what will be, if all those cars, put all cars together, make one huge car, and all trees on Earth put together make one huge tree, and that huge car hit that huge tree. What momentum this supercar have? Mass times momentum, so it will be 2 times 10 in the power of 12 Newton seconds. No, and let's say the time of the collision. That was initial momentum, and it stops, so final momentum 0, so that will be changing the momentum. And let's say time of the collision will be 0.5 seconds. So let's find what force will be exerted on Earth. Force times time equals change in the momentum. So F times 0.5 equals 2 times 10 in the power of 12. So force will be equal 4 times 10 in the power of 12 newtons. Now let's find what acceleration will Earth get as a result of this. Yes?
Has it 4 times 10?
Under 0.
2 divided by 0.5 will be equals 4. If I don't remember exactly the mass of Earth, but I remember the order, so let's say 6 times 10 in the power of 24 kilograms. Let's find what acceleration Earth will get under this force. Acceleration equals force divided by mass, so equal 4 times 10 in the power of 12 over 6 times 10 in the power 24 will be equal 6.7 times 10 in the negative 13 meters per second squared. So even all cars together will hit that one huge tree, because Earth has so huge mass. The acceleration will be so small that it will be undetectable. So that's why when car hit a tree and stop, its momentum passed to the Earth, but we cannot observe it. Yes?
Is that how like earthquakes happen, when there's like a massive amount of momentum?
There is no momentum when earthquake happens. What happens usually, there are huge plates in the Earth core, and they like moving, and one might, I think, coming on top of another. And and then maybe like slide from it. And those plates are huge, they are the size of the continent. So when this happened, it's huge. Then we put some part of, not all Earth shaped, only some part around the area will be shaped. Yes?
If an object has acceleration, meaning its velocity changes, does that mean its momentum changes?
Yes. Momentum changes, yes. Momentum of the single object can change, but momentum of all objects involved will be same.
So it's
Let-
like from like the beginning of the universe, momentum has been the same everywhere.
Pretty much should be. Let's consider example of the collision of two cars. And that's very typical type of the questions which will be on the micro test, on the SAC, on the exam this year.
This is
On
not
the-
on the micro test we're doing on Monday.
No. And I didn't say on Monday, I said next month.
Oh, next week.
It will not be on Monday. So let's consider. We have first we have two cars, car and a truck moving towards each other. So we have a car with a mass equal 1,000 kilograms, moving with the initial velocity of, let's say, 15 meters per second. And we have a truck with a mass, let's say, 5,000 kilograms, moving this direction with a speed of 10 meters per second. And they collide head on. And solving the problems with the collisions, we need to sketch two diagrams. One diagram before collision, and second after collision. Also, question tells that as a result of the collision, they stick together. They stick together. Now, so they will be now as one object. Where it will be moving in which direction? Let's compare momentums of each car initially. So car has momentum 15,000, P0 of the car, P0 of the truck will be equal 50,000. So obviously as a result of the collision, when they stick together, where will be moving? To the left or to the right?
Left.
To the left. So that is final. So this is before, this is after. Now, when they stick together, what is the total mass?
6,000.
You will have 1,000 plus 5,000. Question is, what will be the speed with which they will move?
0.
No.
So, first of all, now next step, we need to choose direction. Momentum has direction. So we must decide which direction we take positive. Which direction will be wise to take as positive?
The left.
So the left, yes. We'll take left as positive. So initial momentum, total initial momentum will be momentum of the truck, 50,000, minus 15,000. Why minus?
Because it's pushing the other way.
Because we have positive to the left. And what the direction of the momentum of the car?
Negative.
To the right, which is negative. So equal 35,000 Newton seconds. And final momentum will be total mass 6,000 times unknown velocity. Times unknown velocity. And law of the conservation of the momentum says final must be equal initial. So we will have that 6,000 V. So we have final momentum equal initial momentum. 6,000 V equal 35,000. So V will be equal 35,000 divided by 6,000 that will be equal 5.83 meters. No, let's round to one that's wrong place. 5.8 meters per second. Can you please check if I divided correctly?
Yeah.
So they will move with the speed 5.8 meters per second to the left. Make sense?
Yeah.
There is one more thing related to momentum, to collision. Elastic or inelastic, collisions can be elastic or inelastic, but we'll cover it another time. And the last thing that we'll cover today before you will start working on the solving problems, we can, if force constant, Ft equal change in the momentum, so easy we can apply it. But what if force is changing? How we approach this type of question? But before I will explain then, this formula is a basis of which safety device? Of which this formula? What do you say? Airbag. This is a formula. Airbags works on this formula. Because when collision happened, this is out of your control, changing the momentum. Your mass times your speed, and then finally zero, you can change when collision happens. So this is given by this due to the speed with which you were moving. But amount of force we can change. How? If you make time of the collision bigger, what will happen to the force? Becomes smaller, because this constant, changing the momentum given, is determined by what speed you were moving. So what airbag does, it's immediately inflated, and instead of hitting some hard surface, and the time of the impact will be very, very small, this will be very small and force will be so very big. But you hit instead the inflated airbag, which relatively slow deflates, increasing many times T, and so decreasing F. So principle of airbags based on this formula. Make sense? So physics saves lives. Now let's consider the last bit for today, the variable force. If we have force changing over the time, let's say something like this, we have a graph. How we can find change in the momentum? It will be area under the graph. Change in the momentum, when we have force against time graph, we can find change in the momentum as area under the graph.
How do we find the area of that?
No, from this particular shape we cannot, there's no any known numbers at all, but in such types of questions, when you need to find area, you will have a grid, and you count the squares on the grid. So you don't get exact area, you can find approximate. To find exact area, if we have formula how the force changes over the time, the exact area will be equal, you need to find integral of f dt, which doesn't tell anything to anybody in your class yet, who doing methods 1, 2, soon will learn about this sign, integral. Others who will be doing methods 1, 2 next year will learn about that in term 3 next year. And That's all for today. Like, subscribe, and donate to help stop Russian fascists.